Oh boy, I think I need to record the second season. Hi folks, welcome back to the Frontend Engineer channel. This is the continuation of the system design series that I started a year ago, and today we're going to explore the Google Sheets, how to design the Google Sheet from the UI perspective, which algorithms we need to use to resolve the cell dependencies, and so on. So it's gonna be interesting. But before we dive into the topic, please subscribe to this channel. Also, you can find the link to my Telegram channel where I post like my personal notes about career, work, and so on. Also, I have a Medium account where I post some engineering articles, so feel free to subscribe. Yeah, and let's start. So before we go into the problem analysis, let's just do the quick overview. What is the Google Sheet? Google Sheet is the spreadsheet system where you can, which you can use for actually many things. It's actively used in the data analysis. You can build the financial planner. It's basically the table where you could put some data and do the calculations. For example, you can say that the cell C2 will be equal to A plus B, and so on. And you can build pretty complex spreadsheets for different type of things. Usually people use it for financial reports, budget tracking, and so on. So as you can see, also the Google Sheet supports different type of formatting. So it's basically you can make cell bold, you can make it striker. Also, there are different types of cells. The cells can be like the date type, number, and so on. So we're gonna try to design not exactly the Google Sheets, but at least like the basic of that. So let's dive into the draw.io. So today I'm going, my schema will be already like populated. So to save the time for the video, yeah, I'll share the schema in the YouTube link in the description. So this time I saved it on the Google Drive, so you will be able to access it. Yeah, let's start quickly with the general requirements for our application. So we definitely want to create safe and edit spreadsheet, and we want to support basic formatting like the bold, inline, strike-through text, and so on. There are many types of the formatting, and we need to think about how can we make it in a generic way. So the new type formatting can be easily supported. The next thing is how do we support the large spreadsheet size? So the default size is 1000 rows and 26 columns, which refers to the number of letters in the English alphabet, but we should be able to extend it. Also, we need to support the formula parsing. So the basic formula parsing includes reference to the cells, and also the dependencies on other cells. And this is going to be a pretty complex topic because this can be done in a multiple ways, and we need to use the right algorithm here. And also we want to like change the column and row size. That's pretty basic. And yeah, I would stop here on for the general requirements, and because this is already a lot. And if we dive into the specific requirements, like how our application should function on the devices, I would expect that the Google spreadsheet should work on the wide range of the devices like tablets, phones, laptops, and so on. And we need to think about the performance in this app because we want our Google Sheet to feel like offline app. So the user don't expect so user don't see many loads, placeholders, and so on. This means that we want to have the PVA mode and the excellent DOM performance. So in order to efficiently execute the calculations and also support creating, saving, and editing the spreadsheet, we need to think about the effective state management and storing this and how we store the data inside. And also we are expected to think about accessibility. The accessibility topic for the Google Sheet is pretty complex, depending on how we organize the elements and what approach we're gonna use. I will explore that in the in the further section. So yeah, I think this is enough for requirements, and let's go to the action plan. So the action plan is basically how we're gonna execute our design. And first we'll do a quick problem overview. So then we try to choose the fundamental design approach. So this can be like HTML and canvas rendering. Then we quickly go through the components architecture, how it looks like on a high level, and then we jump to the how we render the columns and rows, how do we support vertical and horizontal virtualization, and then state management and data model, formula parsing, different type of optimizations, and accessibility. So this is our plan for this system design. All right, let me check quickly if I started the recording actually. Yeah, it started. Yeah, let's jump to the design. So if we do the quick mockup and overview, so in the basic scenario we have the control panel, the columns and rows counter, the grid with the cells. And if we quickly analyze this layout, we see that it's possible that we can have the horizontal and vertical virtualization. So, and before we dive into that, yeah, let's decide how we're gonna build the Google Sheets, because there are two fundamental approaches. Depending on which one we choose, the design can be completely different. So design consideration. So in terms of the design consideration, we need to choose the engine for rendering. So, and this could be there are two approaches here. We can use the canvas approach, or we can use the standard rendering with the HTML DOM elements. Each of this approach has different pros and cons. So we'll start with the canvas. So the canvas is the GPU accelerated rendering, meaning that we'll have no problems with rendering many elements at once, better performance on wide range of the devices, possibly the best FPS for the app. The cons of this approach is that it's a completely different methodology of the development. It requires an abstraction over canvas primitives to render UI. And this means that we probably need to build a primitive library to help the developers develop the app faster. And it's also much more expensive in terms of the costs, because we need specific engineering skills and also more onboarding time for engineers to work with the canvas. And also accessibility can be a real challenge, because the canvas is just the pixel UI. You basically draw the stuff on with the pixels, and you will need to use the mix of the DOM and the canvas layers to enable the accessibility here. So in terms of the DOM approach, so it's easy to develop because it's standard paradigm that any engineer can use. So accessibility is much easier with the right tag use and area attributes. So it's also cheaper for development. But on the other side, there are like significant cons here. So performance probably will be affected because the large number of DOM elements certainly will create memory and CPU load. Comparing to Canvas, when you just draw the pixels, it doesn't create any load on the memory, because you don't store elements when you draw the canvas. You basically use your GPU to draw these pixels on the UI. And also the virtual, horizontal, and vertical vertical and horizontal virtualization can be problematic to implement, because it's really hard. You'll need to think thoroughly to understand how you can combine both virtualizations. And yeah, on the high level, I feel like it's a real challenge. All right, which one we're gonna choose for the design? So depending, it actually depends on your on the company you work for. If you try to design the industry solution that's gonna be used by millions of people, and you expect that you're gonna sell it, or the company has many resources to develop that, I would go for the canvas approach. If you build something internal that's gonna be used by internal people, and you don't expect many functions inside the table, and you still want to build like internal spreadsheet, then the DOM elements approach would be better, because you can save the costs on the development a lot here. It will be not that performant as the canvas, but it's much cheaper and easier and faster to develop. So for this design, we're gonna go with the DOM elements approach, because it's what most engineers can do. And the canvas approach, it's harder. It also requires different set of skills. So we're gonna go with the DOM elements approach. All right, so let's look just quickly at the high-level hierarchy of the components. If you go on an interview and you ask to do any system design problem, please don't draw this stuff on the system on your interview, because it's usually useless. You basically lose the precious time and don't focus on that. For this video, I'm going to show you just a high-level overview of the components, just to have a better understanding of what we're trying to build. So basically, we have the sheet app root, where we will have the table editor that will contain the control panel and the cell cluster. Cell cluster is basically the set of rows and cells. So this is the high-level hierarchy of the components. I'm not going to focus a lot on that. So let's just jump into the virtualization design for that. So if we think about the virtualization support, first we need to start with the analysis, where we can make some trade-offs. If you look at in our table, the standard number of element size will be like 26 column multiplied by 1,000 rows, which is 26,000 cells. So the vertical virtualization is required because number of rows can be more than 10,000. This means that we definitely need a vertical virtualization to optimize the DOM performance. The horizontal virtualization, on the other hand, is not required, because 26 column is a default size. That can be, maybe we can extend it till 72, and we can put the constraint on the app. So this will simplify the design significantly, and also most of the users will not need more than 200 columns, for example. So I would pick 72 columns, like maybe even the 78, like free alphabet size, which should be enough. So, and this means that we will just need to provide the vertical virtualization, and it should eliminate most of the performance problems, or at least make it much better. All right, in terms of the high-level virtualization design, we'll have the constants that will define how many elements depending on each screen size we show in the table. For the phones, we would go with the 50. For the tablets, we would go with the 100, and for the laptops and the desktops, 150 and 200 respectively. So this is the page size, means that how many elements will load when we scroll down and load the next chunk. So, but it will, as I said, it will be dependent on the viewport, but we'll also have the limit variable. The limit variable defines how many elements can be on the screen at max. Means that, so, and if we choose the limit as the page size, so this will feel bad in terms of the user interactions, because each time you will load a new chunk, you need to remove the old chunk, and the user will see the how basically the previous elements are removed from the DOM. And to eliminate this issue, we want to use one page size as a buffer. So this means that the elements that are not is not in the viewport at the moment of the user, we'll use them as the buffer, and we'll take these elements and then later update them and move them down. So let's design our virtualization. To design the virtualization, we certainly need the upper intersection observer and the bottom intersection observer. These observers will listen to the basically will detect when the user viewport touches the element. So if the viewport touches the bottom intersection observer, this means that we need to load the next chunk of data and show it. If it touches the upper, this means that we need to render the previous page of the elements. Also, the next thing that I'm drawing here is the content height. The content height represents the total number, like the total size of the loaded rows. So the more rows we load, the more like the scroll bar should be. And we need to preserve the content height when we scroll up, so the user would feel user wouldn't see that the main container size changes when we go up. All right, so this is the basic setup for us. Also, I want to note that we use the absolute positioning for the elements of our table. Why? So when we do any DOM operations over elements, this creates a thing called reflow. The browser would require to recalculate basically the all dependent elements, and the reflow is pretty costly operation to do. That's why we use the absolute positioning. Absolute positioning will create a separate stacking context where we keep all our rows and columns, and we will do the CSS transformation to optimize the performance, because when you do the CSS transformation over absolute elements, you basically move pixels on the screen, and it will not trigger the reflow and will optimize the general performance of the scrolling. All right, so what happens when the user touches the bottom intersection observer? So the viewport, we scroll down here, as you see, the user touches the bottom observer. This means that we trigger the callback to render the elements. So the elements are rendered because we set the limit of the elements like 2 page sizes. There will be no recycling. So this means we just render the more rows on below. So as you can see now, the row 1 to 10 are in buffer. This means that right now they're not active. The user viewport is on rows n to n multiplied by 2. So these rows are not visible and hidden by the scroll, and the content height is increased because we now have more rows in our screen. So what happens if we load one more time? So it means that we're loading the third page. When we load the third page, it means that we actually reach the limit. So the limit is reached, and we can store more elements and show it on the screen. This means that we need to recycle the previously rendered elements. How do we do that? So we take the elements in our buffer zone here. It will be like row 1 to 10 if the page size is 10. And we use these elements we update the data of these elements with the data of the third page. So we basically take each element, and the row 1 will become the row 2 multiplied by n, then the row 2 will become row 2n plus 1, and so on. So we update the data, but instead of like rewriting the whole DOM element, we're just reusing it. We basically do the soft write, and here's the difference between the hard write and the soft write. So the hard write is basically replacing the whole render tree. So imagine that we have a table, then the row, then the cell, and the cell content. So if we do the hard write, we replace the row, cell, and the cell content. If we do the soft write, we just reuse the cell content and replace only the text nodes. The DOM operation is one of the most costly operation that you can do, and most of the virtualization libraries do this approach. You basically provide the update function for your cell content, and you update the content inside. This significantly reduces the number of the DOM operation, and also improves the CPU performance, and also the whole the rendering performance. So also this is something that all libraries that do for you, like React, Vue, Angular. They all have this reconciliation mechanism that they use. But because this is designed as framework agnostic, we need to think about this too. And this, and we're gonna design our own virtualization mechanism. So what happens once this data is updated? We're gonna move them using the CSS transform. In this case, this is translate y. We're gonna take accumulated height from the row 1 to 10 and move these elements by the number of this height. And these elements will be moved by the CSS transform. So basically it doesn't trigger any reflow. We just basically redraw the pixels on the browser. Also, we need to move the intersection observer at the bottom, and also the upper intersection observer would go to the new first element in here. When we move elements here, we actually change the content height. Means that we need to somehow simulate that we loaded more elements. So the browser would feel like we have more elements in the main container, and the content height is increased. So for that, we need to create artificially added height. And how can we do that? We basically can create a simple div here, or we can just push the padding or margin at the bottom. This space will reserve the space of the moved elements, and this helps the browser to detect the correct the container height that can be used in the calculations of the virtualization. By the way, if you want to understand how to implement it on the coding side, I have an article on that, and here is the link. Go and I start in this article. I'm starting from scratch, and implement the virtualization step by step. You can do that, and you'll understand the whole approach here. So as you can see, we create the empty space on the top, and also move the upper intersection observer to the new first element in our grid. So the elements are updated, they are moved, and we have our updated grid. And we do the same thing when we go, if we scroll up and viewport touches the upper observer, what we do is basically we will move these elements back to the top, and instead of creating the space here, remove the space from the top and create the space from the bottom to preserve the content height. This is how the virtualization would work for us. I hope it's clear now. And now we design the virtualization mechanism for the vertical scroll. So the next topic is formula parsing and how we calculate the cells value. So before we dive into dependency resolving, I want to explain one thing. So all the dependencies in the Google Sheets are represented by directed graph. So the directed graph is basically the graph where each vertex has the directed edge. This means that the edge has a direction where it goes. And also the sales values represent a directed acyclic graph. This means that all vertices has the directed edges, and we don't have any cycle dependencies by default. So the directed graph is used in many dependency system like the NPM or Maven or so on. So, and it's great to represent the graph is great to understand how the dependencies are organized and so on. So because we need to support the dependency linking, meaning that each cell can depend on other cells and other cells can depend on other cells, we will have exactly directed graph. And here's the example formula. So we basically can have the C1 which equals several cells, and then each of these cells can also equal to some value. So to represent that, we'll use the graph. And we need to support the mathematical operations over the linked cells. We also need to support the cycle dependency. So for example, if each one cell depends on another cell and this also cell depends on the previous cell, this means that we need to show the error to the user that it's impossible to calculate and please resolve the dependency. So we also need to provide the effective cell access. Means that these cells should be easily accessed from the state management perspective to enable effective calculations. So solution: how actually we resolve the dependencies in our Google Sheet. So to resolve the dependencies in a sheet, we're going to use the directed graph. Here is the example of the directed graph. And so how can we understand the order? How should we execute the calculations of on the cells? For that, we can leverage the top sort algorithm, which means that the edges are going to be topologically sorted. So we're going to sort the dependencies in topological order and execute the calculation in that order. So top sort algorithm also allows us to detect a cycle. In this case, we show the error of the calculation. So let me dive into the topological sorting. So if we just write this formula and draw the graph like a normal graph, you'll see that from this graph we'll not be able to really understand how we should proceed with our calculations, right? So, but if we sort this graph topologically, we effectively enable this schema. So this the topological sorting is the great algorithm for understanding how to organize our dependencies and how we should go for our dependencies to finish the calculations. Enable imagine the school subjects. For example, to take the higher algebra, you need to first learn the basic algebra. To take the basic algebra, you need to learn the basic arithmetics. And this algorithm will help us to detect the correct ordering of the dependency calculations. And from here, you can see that first we need to take the D1. So I marked so the circles are colored if they have any dependencies. So from this algorithm, we can see that first we need to take the D1, then we go to A1, and then we calculate the C1. So, and let me give you the official definition of the topological ordering. So the topological ordering is the ordering of the nodes in the directed graph, where for each node A to node B appears before node A in the ordering. So the complexity of topological ordering can be found in the O v plus e time. So, and if we look at this schema, so for each node A to node B, for each node A to node B should be so node B appears before node A in the calculation. Actually, I think I made a mistake here. Yeah, all right. So, and basically, this means that first, in our topological order in this case would be that we need to calculate the D1, then we take A1, and then we take the C1. This will be this is the power of topological ordering. So, and also what happens if we have a cycle in our graph? So topological ordering will enable us to find this cycle, and let me show you an example. Here is just a simple example of the possible cycle that we have. So the C1 would equal to A1 plus B1 plus D1, but D1 would equal to B1 plus C1. So this is cycle dependency. Let's draw the graph here. We see that there is a cycle. And if we try to find the topological ordering here, we'll see that here we have a cycle. And the rule of the topological ordering is broken here. Why? Because according to the topological ordering definition, the node A can't be the parent to node B and the child of node B, because it breaks the topological ordering. And using this ordering, we can easily detect the cycle in our calculations. And if we have a cycle, when we do the calculation, we just break this calculation and show the error for the cells that are affected. So this is the topological ordering. I will leave the link to the topological ordering video in the description. Feel free to check this out. But this algorithm is an effective way how can we resolve the dependencies and how can we implement them. So what next? Next, let's understand how we're gonna parse our formula. If we look at the high-level formula parsing, we need to support multiple functions. There are many functions in the Google Sheet. And yeah, first of all, we'll have a dependency resolver module. This basically module that will execute the DFS top sort algorithm on the cells and return the string that will basically parse the return a string that we need to execute by the formula parser. So the formula parser will take the string as a tokens, and execute each token. So the formula parsing can use different arithmetical algorithm. Dijkstra or Schattenyard are the examples of that. We'll not go through this implementation because we can leverage it by the standard library, or we can implement our own algorithm. So let's say we have some kind of the module that parses the formula, and then when the parser splits the string into the tokens, if it meets any function from the function mapping, so we'll have our function mapping stored as a separate JS files. Each name of the function will refer to the JS file. Once we meet, if we meet the function name, then we go to the function mapping and take this file and import it dynamically. This means we will not import the functions that we don't need at the moment, and this will create less, so we will load less code by default, which is nice. And yeah, let's go to the state management. How we would start the calculations of our data. I prefer to keep the state as simple as we can. So for a table state, we'll have the flattened map where the key is the row, the concatenation of the row and column. and the value is the table cell. The table cell type will have the formula. So the formula is the row string that the user enters to calculate the value. The calculated value is a resulted value. This means that it can be null on the table initialization, but once we calculate this value, we're gonna use it here. We can set the value of the cell in the state. Also, we have a type. There are different types like date, numbers, and so on. We're not going to dive into the cell types because it's not the purpose of this design, but I'll touch a bit on the formatting. So the formatting options, they can be many formatting options. I would suggest using the enum here. So for each formatting option, we'll create enum name, and will not depend on any class names or any class names and other things. So basically we will be dependent on the formatting option, and when the application advances, it's become more complex and so on, class names can be changed. Implementation for each formatting option can be changed. So in this case, we will not change the formatting option on the enum level. We can only change the implementation of the formatting option in the code level. This means better supportability, and we will not be dependent on any class names. We don't want to store any like class names on the state, because imagine that some class names are outdated and we store it in the user state, and maybe we want to import the new file. So we will need to maintain the mapping of the old class names and so on. That's why I prefer to keep using the just enum and not be dependent on any like specific implementation. So when the table cell changes, we'll catch event on the top level on the table. So we will have a listener on the high level table. So when the user do any changes over the cell, this will be triggered from the cell to the table, because all events are bubbled, and we're gonna catch them on this level, and we're gonna determine on which cell the event is fired by having the data attributes on the table cell. So we'll use the row and column for the cell. So we will determine the changes over on the cell, and then fire the on cell change. So then we access the table state by row and column, and then we take the formula, and basically we starting our calculations from the dependency resolver, then the parsed string, then we parse the formula, and then do our arithmetical operation over the cell, and so on. That's how we going to calculate the dependencies. So the next step is optimization. So there will be no network optimization section here, because we expect that this application will work offline. So, but in terms of the rendering, I would say that the app should feel offline. This means that we need to use the web workers. And also the DOM. We are using virtualization to help the DOM renderer not to render too much in our browser and maintain the performance. So we do not delete and insert the new nodes. We just update the old one once we have a buffer. Also, in terms of CSS, we keep the naming conventions. We don't use the long CSS selectors, so we optimize it here. We do require minification for the build process. This might sound like obvious, but not everybody do that, and it's better to mention that. So in terms of the JavaScript, so we try to do stuff asynchronously. This means that we can delegate the calculation of the dependency of the table to the web worker. And then once the web worker gives us the data result, remember that we can't pass the DOM nodes to the web worker, and we can't modify the DOM from the web worker. So the web worker can take the data and return and give us the data back. and we take this data and lazily update the nodes. So this way we'll not block the thread, the main UI thread, by the calculations. And also this way we actually, this is the basically we'll not block the UI thread, and that sounds good to me. Alright, so as I said, we're not going to do any network optimizations because network optimizations here might be overhead. If we want to use our app offline, we basically load the resources one time and that's it. So the accessibility. So the HTML5 is accessible by default. You don't want to use the area attributes if you don't need them. So if it's possible, we want to use the accessible HTML elements, so table, TD, TR. But depending on the complexity of the render, sometimes we'll have to use the normal HTML elements like div, section, and so on. So in this case, we need to mark our table with the role grid because we expect interactivity from the grid. We also want to mark the our columns and rows as a group, so to identify where we have the call header and so on. And also we want to set the row and cell to the attribute to the div, so the browser knows that we are at the cell and the screen reader can access this. All right. So in terms of the visual optimization, we don't want to use the pixel values in our, because when if the user has any custom settings on this means that the user will have to, so the UI will not scale, and we don't want that. And in terms of keyboard navigation, shortcuts are required. We need to prepare the list of shortcuts, and also if possible we want to implement the search. I think that's it for, the accessibility topic is pretty complex, so we can speak about that a lot, but depending on how you want to dive deep into that, it can be different. All right, that's it. I think we're done with the system design for Google Sheets. In this design, I didn't follow the timeline because I've decided that it's better to keep everything on the screen and save the time on the drawing. So, and also I try to explain the concepts more in detail, so we are not restricted in time. So I hope you like it. Let me quickly switch to to myself. Just a sec. So I hope you like this video. The next video will be about the system design of the Google Calendar. We're gonna look how can we design the Google Calendar from the multi-user perspective, from the UI perspective, and so on. This is also was one of the highly requested topic from the comments. So thank you for your comments on my YouTube videos. Thank you for your support. Please subscribe to the channel, and if you like this video, or even if you don't like this video, comment out, and suggest any topics that you want to explore in the next videos. And I see you in the next one. Bye.